Yes, I'm here. Hi.
Yes, I hear you. Hi, Petr. So I think it's time to announce our today's talks. We have two talks, both from Mathematical Institute of Opava University. The first talk will be by Hinek Baran, who will tell us about the JETS computer system. Hinek, you are welcome. And I kindly ask everyone except for Hinek to switch off microphones.
Okay, thank you very much.
Okay.
So, hello everybody. I hope you can hear me. My talk is about the computer algebra package JETS, and I will try to give you some light introduction in order to learn you how to use this package, and maybe I will answer some of your questions. Everything I will speak about can be found on the homepage of our JETS package. The link you can see on the first line of my Maple worksheet. So you can click. Oh, sorry, you cannot click. You can write it in your browser and see. Okay. So what is JETS? JETS is basically a set of Maple procedures. And those procedures are to facilitate solution of differential equations in total derivatives on differentials. So we can say that JETS is just a Maple tool to compute symmetries, conservation laws, zero curvature representations, recursion operators, or some other invariants of systems of partial differential equations. It is just the one single text file where all the procedures are stored. And how to use it? You have to start your Maple session, as you can see on the screen, and you have to put the file jets.s into your current directory. Once you have it.
Hinek, a question: what version of Maple should we use?
Mm-hmm. I'm using Maple 2015, so my recommendation is Maple 2015 or never, but it's supposed to be compatible up to Maple 17. But well, I'm not using Maple 17, so maybe there will be some trouble. Let me know if you find some sort of troubles. I'm trying to, after every change, I'm trying to make sure that it is Maple 17 compatible, but well, I'm not pretty sure. I'm just almost sure. But 2015 is the best option, or never. So once I have my worksheet opened and once I read in the file jets.s, I can use my jets package. It works on differentials, but first of all, I have to specify what coordinates I'm using. In order to specify the coordinates, I use the command coordinates. It has 3 arguments. The first argument is a list. It is a list of base coordinates. The second argument is a list of fiber coordinates. Of course, there should be just one single item in this list, as in my case. I have independent coordinates t and x, the first list, and I have a dependent coordinate u, the second list. And the third argument is a number, it's an integer, and it is a jet order, it is a maximal jet order I suppose to see in my calculations. As a result of this coordinates command, I obtain something like a sequence of symbols, and those symbols are jets. So if I want to specify a jet of the coordinate u with respect to t, I can see in here it is u underscore t, u with respect to t. If I need to use, say, third jet UTTT, I can use u underscore TTT. But if I want to use, say, fifth order jet, I can see in my sequence it's u underscore 5 and t. So if you're not sure, don't mind what is the reason for this. It's you can just see the result of the coordinates function call, and in this sequence you always can see what is the correct syntax of your jet variable. Internally, jets are not symbols, but they are unevaluated function calls. So for example, a jet of u with respect to t is a function call of the function jet, and the arguments are u and t, u with respect to t. As a result of such a function call, I obtain the symbol u underscore t. So this u underscore t is, say, shortcut for the more complicated unevaluated function call jet ut. As a second argument of this unevaluated jet function, it's a monomial. So let me show you an example. The jet of u with respect to t and xxx can be written down like this, and so on. So I have two possibilities how to write down jets. I have two options how to write my jet variable. I can use this unevaluated function call, or I can use this underscore syntax, the shortcut. For example, if I try what is jet of u with respect to x times t minus jet of u with respect to t times x, I obtain 0, because those two monomials are obviously the same. X times t is the same as t times x. But if I use those shortcuts with underscores, I get trouble. I get in the trouble, because the symbol u underscore xt is a different symbol than u underscore tx. And just one of these symbols is the correct shortcut, and the other is just a symbol with no meaning. If I'm writing my code, if I'm doing my calculations, and if I don't know which order is correct after this underscore, I have to look back to my coordinates command. The order is the same as specified in the list which I given as a first argument. But if I'm not sure, I can see what was the result of the coordinates command or function call, and I can see the proper syntax. I can also do some tricks with the jet function C. I can, for example, generate easily some possibly long sequence of jet variables. Instead of writing it manually, instead of writing manually u_x, u_xx, and so on, I can generate it programmatically. Okay, so we have coordinates and we have jets. The other important object is total derivative. How to deal with total derivatives? The capital TD is a function which represents total derivatives, but they are not evaluated. For example, if I write down, well, maybe if I write down something like that, I obtain total derivative of f with respect to x, and the second argument can be also monomial, the same monomial as in the case of jets. So the result of TD, of the total derivative, it's not evaluated, it's a total derivative itself. But on the other hand, total derivatives are differentiations, and all the linearity and Leibniz rule and so on is respected by the TD function call. So see the example. If I give as an argument a sum of two functions, I obtain sum of total derivatives, and so on. The same with Leibniz rule and some other special functions. Okay, but how to evaluate total derivatives? How to obtain the result? In order to evaluate total derivative, in the case when in the argument is some function, I have to tell what my function depends on. I cannot compute explicit form of total derivatives unless I specify on what variables my functions depends. So in order to specify the dependence, I have a dependence function call or command. So now I set that my function f depends on t, x, u, and ux. Now, total derivative is still the same, not evaluated, but by using the function eval_td, I can evaluate such an expression. Okay. Say I change my mind and I allow f be dependent on second jet, uxx. In such a case, of course, I obtain a different result according to the dependence I specified. As you can imagine, total derivatives are very long expressions. So the reason why I have explicitly called evaluation of total derivatives is simply that I want to prevent my memory of being out. So if I want to see explicit form of total derivatives, I have to specify what my functions depends on, and I have to call eval_td function. What about partial derivatives? partial derivatives has a function PD, lowercase, so with the same arguments as before. So the first argument is a expression to be differentiated or function to be differentiated. The second argument is a monomial. And I can easily change the monomial as I like this. Okay. What about partial derivatives of total derivatives? Maybe the example is better than long. So you can see Jets knows what are partial derivatives of total derivatives and respects all the rules. So without evaluating total derivatives, I still can see what partial derivatives of total derivatives are. Let me show you some simple example. I want to verify whether the expression A, where k is just the constant, by the way, if I want to specify that something is a constant, I can do it by this function call. I will say that it's dependent on empty list of variables. Okay, so A is a candidate for a solution of KdV, but how to check? Okay, so I assign to A my expression. I can store KdV in the symbol KdV. And now, well, I have what I want to do. I want to substitute my solution into KdV. So let's do it. The result's supposed to be 0, but it's not. Why? The problem is that in my expression for KdV, I have u underscore t, which is a shortcut to some jet, but it's not u, it's u underscore t. So if I use my subs command like this, it will not substitute for u in this KdV. There is no u in this, there is one u in the KdV, just this one. But the jets of u are not substituted. So this is a wrong way to do it. The problem can be solved by the function convert. I can convert my KdV into total derivatives. So jets, those underscores, are replaced by total derivatives if I use such a command. And I can simply say that I want to substitute u to A. If I run such a command, I obtain, well, it's still not 0, but the second problem is that not every time I can see 0 immediately. Okay, in the first case, if I used the subs, that's the wrong way. If I use this convert, I obtain the correct result, but I have to remember that I have to some simplification, not necessarily simplify, but I have to normalize in some way the result of my conversion. So those example was an example of conversion of jets to total derivatives. What about partial derivatives? Let's, for example, I choose very extremely simple example. Let's try to solve such a problem. So let's say, well, I'm looking for a solution for such an equation, but let me delete it. Now I can evaluate total derivatives. I can see what is inside this capital E. As you can see, my E is expression consisting of partial derivatives of f and jets of u. Okay, so just for curiosity, I can see what's, say, inside. I can see that this expression is represented as differentiation of my f, blah, blah, depending on blah, blah, blah variables, and so on. So, well, I can maybe use PDSolve to solve this equation. By equation, I mean that this expression is supposed to be 0. Okay, so let's try PDSolve. Maybe it can help. Oh, no, what happened? Well, what happened is that my u underscore x and u underscore xx and so on, my jets, are not symbols. They are unevaluated function calls of the function jet. So in order to use PDSolve in the same worksheet, I have to substitute my jet variables and replace them by some new unused auxiliary variables. See here, see here. I can substitute ux should be, for example, u1, uxx should be u2, and if I do such a substitution, then my PDSolve doesn't giving me my result, but not even giving an error. Oh, okay. But the problem is fixed. I have no jets in the expression to be solved in the PDSolve command. Okay. Now, I said jets is a tool to work on diffieties. So what about diffieties? Say I want to compute some object on KDV, for KDV. So I will read. So I'm starting a new worksheet to be clear. I'm reading again in my jets file. I'm specifying coordinates. So tx on the base, u is a dependent coordinate, and I will maybe obtain 6 order jets. So this is the 6 as the third argument. And now I can specify, okay, let's work on KDV by the command equation. On the left hand, in the argument, on the left-hand side, I have just one single jet. On the right-hand side, I have some expression. I will say a little bit later some restrictions. So once I issue this equation command, what is ut? Well, ut is the right-hand side of the equation I specified. What is utx? It's an x derivative of ut, and so on. So, but uxxx has no some specific assigned value. uxxx is just uxxx. So I obtained the symbol uxxx, or more precisely the jet of u with respect to xxx. If I change my mind and I want to have u free x on the left-hand side, I can try to do something like that. Oh, error. What happened? Well, I already assigned some expression or some value to ut, and now in this function call I'm using this ut, but ut has a value, so makes no sense. I can try use apostrophes like here. Maybe it will fix my trouble. But still, it's not good, because there is a confusion between UXXX and UT and so on. I can fix it if I use apostrophes also on the right hand side. But more better is to do 2 steps. In the first step, just clear all the equations. So I will make sure no assignments to jets I have in the computer memory. And as a second step, I can issue my KDV resolved with respect to the UXXX. Now, UT is just UT, but UXXX is the right-hand side. As you know, I cannot resolve my equation arbitrarily. It must be resolved with respect to a leading derivative, but this is a common thing, so I will not comment it more. Okay, so on the left-hand side, there must be a leading derivative. Well, let's do some other attempt. I cannot, if there is no leading derivative on the left-hand side, you can see I obtain an error. If I do it by mistake, I can clear and then continue. By clear, I mean I can call equation with an empty argument. The next important property of the equation command is that in this right-hand side, there should be also some function. First of all, in order to have a free function on the right-hand side of my equation, I have first of all specify what my free function depends on. So, okay, I will say f is dependent on x and u. And now I can introduce an equation where my f is on the right-hand side. Now, what is UTX? Well, UTX is some expression where I have my free function f and its partial derivatives. But maybe I will change my mind and I will see that f is x times u. What is UT? So I can assign to f x times u. What is UTX? Oh, still f here, but I assigned the value to f. What happened? Well, JETS doesn't know about this assignment. I can evaluate, or I can call function refresh. Function refresh tells to JETS, tells to the computer that something changed. For example, my function f on the right-hand side of equation has changed, and once I call refresh, the result is correct. Okay. So now, just a complex example. Let's try to compute symmetries of KDV. So I will open a fresh session. I will read in my JETS file. I will specify the coordinates and equation as before. And now what I'm looking for are solutions of determining equations for symmetries, more precisely for their generating functions. in order to just obtain those determining functions of symmetries, I can use the function symmetries with an obvious arguments. With every dependent variable, I have some new function, say capital U. So this symmetries command just generates the determining equations in total derivatives, of course. By the way, if I want to look for conservation laws, or more precisely, if I want to look for cosymmetries, I can use such a function, laws. But right now, in my example, I want to compute symmetries. So let's concentrate on symmetries. The capital U is smooth functions, which can depend on a finite number of variables. But I cannot make some general computation. I have to say what variables my U depends on. So, okay, let's look for symmetries up to the 5th order. So I have to say that my U is dependent on all the jet variables up to the 5th order. I have to say to the computer that U is unknown function. I'm looking for U, so I have to say it. And now I can say run. And as an argument is an expression to be annihilated. So let's see. I have to wait a moment. Maybe 2 moments. But hopefully not too long. Oh, it's working. It's working. Still working. My notebook is not fast, but that's okay. Still working. Still. Almost done. So it's done. As a result, I obtain a success message. In such a case, run succeeded. The function run succeeded. What is the result? Well, I can see what is my U dependent on. So I found some symmetry dependent up to the 5th jet of U. And the result itself can be seen by running such a function, clear PDS. So I converted my equation in total derivatives to this passive form. So in order to find all the symmetries of KdV, I have now solved such a system in partial derivatives only. Well, how to do it? I can look to the system and I can see, well, the highest jet is 5th jet with respect to x. So let's see what I have. I can select some subset. Doesn't help, but still I can see, for example, here the first expression and several next. I can see that U is linear in u5x. The uppercase u, the unknown function u, is linear in fifth jet of u. So I can assign to u, I can assign to u in what form I think it is, or the solution I found. I have to specify what the new unknown functions depends on. I have new unknown u1 and u0. Doesn't depend on u5x anymore. Okay, I can see, I can make sure. Let me see, I have 0 here. That's good. And now I can repeat my procedure. I can specify, well, u1 and u0 is now my unknown function, and I can run again. And so on and so on. I will not spend too much time to show all the steps, but it's the same as before. But finally, I will obtain the result, which is such a u. I have some u1 and c3 is a constant. I can see, for example, here I can see that all these symbols are constants, and I can collect out those constants to see the final result. So I can see this is a symmetry, this one is a symmetry, and so on. I have it. I have the result. By the way, I can compute Jacobi brackets. We have function Jacobi in JET's package. So I can compute the algebra of symmetries as well. Okay. Now, let's to have some idea how this command run works. So how this package works. Just an idea, not a complete description. So let's go back to KDV and its symmetries. And imagine what can you do manually, just with your computer at your hands, but manually, without the magic run command. You will specify what is the equation and what are the coordinates, what your uppercase u depends on, your unknown function u depends on, and you can generate the generating condition on u, but now, what is the length of the expression s? If I don't evaluate total derivatives, it's something like that, 74. If I evaluate total derivatives in my expression to be resolved, I obtain something very huge. Okay, so it's better don't evaluate. Just let's see what variables are inside u, or what variables u depends on. Okay, up to the 8th order. I have jet u8x. It is the highest one. So what I can do manually? Well, I can compute what is partial derivative with respect to this jet. Aha, it's 0. So, well, it in reality doesn't depend on u8x. What about u7x? Aha, I obtained some non-zero result, so I can treat it. I can treat it with that. What about derivative with respect to 6s? So this results can be obtained by issuing just one single command, which is derive, and derive computes what are differential consequences of its argument. So instead of looking what this expression depends on and trying to compute partial derivatives, I can use derive, which finds for me some most simple differential consequence of its argument. So this magic run is just a loop in which we call this derive and in which we compute compatibility conditions. Okay. How to assign two partial derivatives? I will specify my coordinates. Now I have two dependent coordinates, u and v. And let's see an example. So I can say, once again, I can say that I want to assign some expression into the second derivative of u with respect to ux. Okay, so I want to this partial derivative, I want to assign a value to it. How to do it? Well, I can issue such a command. The function called put assigns some value to the left-hand side of the expression in its argument. So now, what is this? Okay. It has a value now. But what about the third derivative? As expected. But once I call this clear PDS we seen in the worksheet before, I also clear this assignment. So I made this assignment, I put something to the partial derivative of u. But once I call this function, it's gone. Okay? And I'm afraid I'm out of my time almost, so I will try to skip some details and go to the last worksheet I have prepared. And this is an example of classification problem. So let me show you. So let's try to find symmetries of such an equation. As you can see, on the right-hand side, I have an free function f depending on u. And the question is, how does the symmetry algebra looks like depending on such an f? So I can try to use, as before, the machinery of jets. So I specified coordinates, dependence equation, okay. My unknown function is, say, capital uppercase U, dependent on second jets. I'm looking for symmetries. U is unknown functions, and to save time, I have prepared it. So what will be the result of the magic function run? Blah, blah, blah. Fail. It's not success, it's fail. Why? It's because of this function f. Jets, or this magic run, is trying to resolve such an expressions with respect to partial derivative of f with respect to u. But maybe it's 0, so it cannot resolve such an expression. In order to handle this problem, I have to say I have two possibilities. Maybe it's 0, maybe it's not. So say it's 0. In such a case, I can issue such a command. I can assign 0 to the appropriate partial derivative of f. And I can run the function run again. And I obtain a result. But this is just the one single fork of my whole computation. The other option is that the partial derivative of f with respect to u is not 0. In such a case, I will use such a declaration. And so on. But my time is over. So let me thank you for your attention. And that's it.
Thank you, GDEq. Questions, remarks? Well, I understand that to follow these computations for the first time is a bit difficult, but I have quite a rich experience with working with jets, and it is useful in many computations related to calculus of total derivatives, not only symmetries and conservation laws, but many other problems. And I strongly advise those one who are engaged in such sort of computations to try and to estimate the quality of the packet. So thank you, GDEq. So our next speaker